Hello everyone, this will be the last ME2761 lecture. It's been a little while since we've had one. This is going to be over failure and a little bit on ethics too. I'll sort of frame what we're going to talk about today through this hypothetical case study. Uh, so let's say you're an engineer for a high-end car company. The company makes a hypercar that's often used in professional racing events. In some recent racing events, there's a piece of bodywork on the front of the car that has worked its way loose. It's not a very critical component, just part of the aerodynamic package, and losing it hasn't created an issue in any of the races, at least yet. Before the next race, you discovered that there's some fragments of the bodywork that have gotten lodged in one of the brake ducts. Here, specifically for the front left tire, you believe that this could affect cooling. Maybe these components get in there, get lodged in, and prevent the components from cooling, and it might lead to a braking system failure, which would be a critical event. So, what is your job as an engineer? And this is one of these cases where this lecture is much better when we can do it in class. We can talk about this for a little while, but what you should do as an engineer, you often get yourself in, not often, but at least once in your career and maybe a few times, you get in a situation where something like this happens, where something's wrong and you got to figure out what to do. And the correct answer, if you're working for someone, is to always go to your boss, always go to management, always go to the person above you. At some point in time, as you rise through the ranks of an engineering company, you're going to be the person in charge, and things change a little bit. But for you all, once you get started out in your careers, you're going to be working for somebody. If you get in a situation where you're stuck and you don't know what the answer is, ask your boss. That's always your responsibility, is to ask your boss. And that's something that, and I've been a professor for 10 years. This is my 11th year, actually. And I run into situations every once in a while where I just don't have an answer for a student's question. And I ask my boss, and, probably gets tired of getting emails from me about stuff like this, but it's the right thing to do. So, consult your boss, consult management on it. So, when things get bad is when you talk to management and they refuse to help. That's when you're in trouble. So, in this hypothetical case study, let's say management refuses to implement a solution, saying there's just not enough time to do it, and it hasn't been a problem. Right? Which in engineering failure, it's not been a problem yet. That is a scary thing that's gotten a lot of people killed. So, car enters the race as planned, no fix for this bodywork shedding issue. During the race, there's TV footage. It shows bodywork fail and possibly entering the brake duct. The car doesn't have any kind of direct way of measuring the brake temperature, which in the real world it would, but let's say there's not any way of directly measuring if the brakes are okay. You don't want to bring the car in because, pit stop, because then you're going to lose any chance of winning the race or placing well. So there's this rumor that there's a competitor out there that has the thermal camera that might be able to see an increase in brake temperature and see if things are okay. You don't really want to talk to the competitor because they're the competition, right? You're admitting a weakness or a flaw or giving them information they wouldn't have otherwise. So what do you do? Again, it's better for having some discussion here, but you've got an opportunity to get data. And yeah, you have to go to a competitor. Yeah, you have to eat a little crow to do it. But you should, right? I mean, there's no real loss other than maybe admitting you don't have temperature sensors on the car, admitting maybe there's a design flaw that your competitor could capitalize on. There's not a big loss in this, so sure, why not? So that, that's something you could bring a case to management and be like, this is, we lose very little and we can gain quite a lot, and this is a situation that's starting to get a little risky. And if you can explain the risk, people will listen. So you pass the request to use the competitor's thermal camera to your team's management. They refuse. So now you're in a situation where you think there's a problem, and you have no way of getting evidence, and the driver's the one out in the car and is going to be the one most directly affected by this. Should you consult the driver for their input on it? I think most of you, based on the discussions I've had using this case study in the past, would say yes, or especially if you were the driver, you would want to know. Management says the driver's a professional and would rather not know and should focus on racing, and if something happens, it happens. During the last lap of the race, the car's brake rotor overheats and fails. At the end of a long straight, the car goes off the course, hits a wall, the driver's killed. After reviewing the failure, after the looking at why this happened, it was determined that the bodywork that caused this whole thing, sort of the root cause of this, that bodywork that was falling off, was completely unnecessary and removed from future race cars. So where's the fault? And I think it should be obvious at this point that it's sort of a tree of faults. In fact, you encounter fault trees a lot when you're trying to trace the root cause of a fault. That's like the 5 whys we talked about a long time ago in quality, where you ask why 5 times to get down to the root cause of things. But there's a lot of different places this could have been stopped. This is hypothetical, but this is based on a real life study that we'll talk about here in a second, or a real life thing that happened where people were actually killed in a very high profile failure. And who is at fault in a situation like this? So is it the engineer that tried and got shut down by management? Is it management? Management's got a lot of things to worry about. So there's not just one engineer that's bringing issues to them. There's not just one situation they have to worry about. So it's a combination of factors. A lot of it, from a legal sense, it gets pretty tricky. And it kind of end up in whoever gets found at fault by a jury or a judge in a bench trial, or what looks bad enough that things just get settled. There's a truck driving by. It gets a little tricky in that, but usually it's more of a management and culture issue that's at fault in a lot of these situations. It's a culture of not addressing problems. It's a culture of not stopping and fixing things. It's a culture of not listening to engineers. It's usually at fault in situations like this. So this was derived from a very real failure. And a lot of people at this point in time say it's Challenger. It's not Challenger. Challenger is an interesting failure that you hear a lot about in engineering school. This is actually the Columbia orbiter. It's a space shuttle, but it's the Columbia failure. So this mirrors a lot of the details that happened in the space shuttle Columbia disaster. So the shuttle was launched on April 12th, 1981. That's literally the day I was born. Flew 28 missions and was lost on February 1st, 2003. All 7 crew members were killed. A little background: in prior launches, 4 specifically, this time that it was known, there was loss of foam in whole or part from the external tank bipod ramp. So this is the big orange tank that holds the liquid hydrogen, liquid oxygen for the space shuttle main engines, connects to the orbiter with this little bipod, and there's this foam ramp on the front of it to sort of make it a little more aerodynamic. It's just I think it's just a urethane foam, but it's just sort of like a spray on and then carved foam, kind of like grate stuff or expanding urethane foam that's then kind of sort of carved into a wedge or ramp shape to be a little more aerodynamic. This foam had been seen to come off. It was common enough that a name was given to it. These were all successful launches. There's a moped going by now. During one mission, 2 launches prior to Columbia's final launch, a camera was placed specifically to understand this problem or this situation, this phenomenon. On this mission, the one that they put the camera to watch, a piece of foam was shed and it struck the left solid rocket booster, leaving a large dent. What should NASA have done at this point in time? And it's the easy answer is they should have fixed it. And that's always the answer in a situation like this, is they should have fixed it. The issue you're dealing with on the space shuttle is it's the most, at the time, the most complicated system on the planet. I'm pretty sure that was the case at the time. They were talking about if not, then one of the most complicated things ever designed by mankind. There's not just one problem that needs to be fixed. There's lots of problems that need to be fixed. There's lots of things that need to be changed. There's lots of things that need to be addressed. So it's always about prioritizing things, and it's real easy to look at failures like this in hindsight and say that obviously this needed to be fixed. But this needed to be addressed. And it needed to go into need to be prioritized with the other things that needed to be addressed. In this case, it didn't. It didn't get addressed. It didn't get fixed. And looking back, we know that was a tragic mistake. So launch. So these videos, I will post links to them in the description below. You can pause this one and open a new tab and watch a space shuttle launch here. And it doesn't look like anything went wrong in that. In fact, the first indication something was wrong was within a couple hours. Some of the footage from tracking cameras was examined. Nothing really seemed too unusual. Higher resolution video was processed a day later, and a debris strike was seen at about 81.9 seconds, in which that's in that video previously on the previous slide. That debris strike happened at 81.9 seconds after launch. And then here's some more footage of the debris strike. You guys can watch that video in a new tab and come back. Details. So it looks like it hit on the. Looks like the foam came from the from the left bipod area of the external tank from that foam ramp. It looks like it hit the underside of the wing near the reinforced carbon panels 5 through 9 in this region through here. Obviously, that was a concern for the review team was concerned about damage. This is one of the most critical parts of the thermal protection system. It's on a leading edge. It's where the temperatures and pressures are at their highest, and it's one of the scariest places to have some damage. Okay, what do you do now? So if you're on that review team, what do you do? Inform management, right? That's obvious. But past that, what are your options? How do you know how big of a problem this is? Because now you have an orbiter it's already been in space for a day. It's got 7 people on board, and it's got a potentially damaged thermal protection system. And your options are very limited at this point in time, very limited. And maybe there's no good options at this point in time. I'll talk about some of the potential options in a second, but really, and that's something that's very common in failures, is there's usually a window to address failures, and the earlier, the easier it is. And at some point, it's going to become very difficult, and at some point, it might even become impossible to address failures. So that's why it's always good to prioritize and fix things as soon as you can when it comes to addressing failures in engineering applications, because at some point in time it's going to be very expensive or very difficult to address them. So try to get more information, right? That's always, if you're dealing with uncertainty as an engineer, can you get more information? Can you get some hard data? So someone had the idea to maybe ask the Department of Defense if they could get imagery from one of their spy satellites. So there's lots of these things up in orbit. Very little real information is known about them because they're about as classified as things get. Supposedly some of these things are on the the Hubble Space Telescope is supposedly based on some internet theories that it's actually a modified spy satellite, and so you're talking about things that are as good as the Hubble Space Telescope that are essentially designed to be pointed at Earth. So I think they're up very high. I don't know what the orbit is on those, but they're in a position where they could probably focus on the orbiter and probably get good imagery. And a request was made. Maybe we can have a spy satellite look at the orbiter and see if there's any damage. Which honestly, it's a pretty out of the box, clever idea. A report was sent to the mission management team, so it did go to management, and a formal assessment was begun. They met. The imagery request was forwarded upwards. The request was denied within NASA, I believe. I don't think it got out. Again, we're dealing with classified things here, so who knows what really happened on it. But anyway, the request from imagery was denied internally in NASA. So without direct data, they tried to make inferences, try to make models to not to see what happened, right? To predict, to estimate what happened. So they use this tool called Crater. I believe it was internally developed. I'm not sure on that. That was not designed for modeling these kind of impacts. Foam on a composite carbon ceramic material. That's a hard impact problem to model. So I mean that's as far as impact problems go, that one's pretty tough. So sorry, excuse me, whatever tool that was used to model that, if it wasn't designed specifically for those kind of impacts, it's probably not well suited to it. But anyway, this crater tool predicted some localized heating due to damage and deformation. Uh, results were presented to the mission management team. This was declared a turnaround issue, as in they take care of it for future flights. Lots of internal emails were bounced around and kept, because as a government organization, your emails are kept. And it's something you should always know in almost wherever you go, your emails are being kept, and in some cases they're being watched and read. I've worked in the public sector for 11 years now, and I think all my emails are public record, and they have to be requested, like the Sunshine Law in Missouri, they can be requested, but those are all kept. Those are all logged. They all can be looked at later on if some kind of incident happens. And when you go work for a private company, it's all up to them. But in most cases, there's going to be somebody recording all of your emails, and maybe somebody's reading your emails, depending on if there's any keywords in there that get tagged or stuff. So it's just sort of the world we live in. Google's definitely reading your emails. So if you're using Gmail, so we live in a world where all this stuff's getting archived, and for failure analysis, it's nice because you can go back and see what happened. But it also means you really can't hide or plead ignorance on a lot of these things. So the communications are kept, and it's something that you always have to be aware of. And it's sort of good to cover your ass at times in email. So it's a good thing. It's just something you have to always be aware of, is that your digital communications are kept, they're archived, and they can be used, they can come back to either haunt you or help you. So now what should NASA have done? Really, I don't know. They've sort of declared this a turnaround issue at this point in time. So they've said that we just can't do anything with it. We can't do anything at this point. So I think the main question at this point is, do you tell the astronauts about it? So this is a response from someone at NASA about whether or not the astronauts should be contacted. So I'll let you all read this, then we'll talk about it. It's a pretty bold statement. And maybe it's true. This is a value decision for the astronauts. They're signing up to be astronauts. They know that there's a huge risk. There goes my dogs. It's a tough thing. Maybe some would rather not know, so they can go on with the mission. I would like to think I would want to know. I mean, if I was an astronaut, I would want to know. I mean, the Apollo 13 astronauts, the failure happened while they were up there, and they knew about it because they were there when it happened. This is a bit of a different situation where the astronauts had no idea anything had happened. They knew about it on the ground. Gosh, you'd have to think it's only fair to let the people whose lives are being risked to know there's an issue, even if there's not a lot of options. I mean, that's something that I just don't know if this can be supported. I just don't know if that's the ethical, the correct thing to do. During reentry, the orbiter was getting through, entering back to the atmosphere, slowing down, generating lots of heat, and there was it's hard to know exactly what happened because it's reentry is such a traumatic, hot process, and it's really hard to get really good solid data during reentry. Um, with the orbiter didn't make it. It broke up, and all 7 astronauts were killed. And that's when the formal accident investigation started, and the orbiter broke into lots of small pieces and some big pieces, and was scattered all across Texas and some of the surrounding states. And at that point, how the best possible explanation for why it happened needed to be determined. So 80-some thousand pieces of debris were found. Data from sensors on magnetic tape that had made it to the ground was retrieved. This was able to fill in some of the gaps from telemetry, and that data pointed to a left wing leading edge failure, which is consistent with where the foam strike occurred. So looking a little more at this area, here is this bipod. Here's this ramp. This would be the foam in question. This is a little more about that. So this is this foam material here. These are actually the metal parts here. I believe hydrogen maybe flows through this. I don't know if hydrogen flows through this connection or not. It's certainly a mechanical connection. I don't know if any fluids flow through it or not. But anyway, this is just to insulate this and to make it a little more aerodynamic than just this sort of blunt edge here. You can see the leading edge of this bipod sees quite a lot of pressure here, the white being the highest pressure, the stagnation point here at the nose, the leading edge of this. But you can see you're starting to get down closer to the boundary layer here, and this ramp's not really that it doesn't have that much pressure on it. So really not a super critical area as close as it is to the tank. So going back and looking at in more detail at previous launches, in 80% of the 79 missions where there was imagery, some type of foam loss. Some type of foam loss was seen. 10% of that from the left bipod ramp, so somewhere around 6 or 7 missions. 30% had no data, so there might be more. Results. Sorry, digging a little more deeper into the structure here. We've got an aluminum structure, a lot of it aluminum. Aluminum is not a high strength, or not a high temperature material, and you've got some ridiculously high temperatures out here on the leading edge of the wing. So there's this reinforced carbon-carbon, which is a composite material of carbon fiber and a carbon matrix, which is a very, very high temperature resistant material. They make that's essentially what the carbon brake rotors are that they use on like F1 cars and things like that. Or reinforced carbon-carbon is one of those materials. Then there's some other really high performance metals like Inconel here, getting into steel, and then getting back here into the aluminum here. So the heat's all here. They try to keep it away from the aluminum core structure. You can see if this was compromised, hot gases would get in here, stagnate, it would get very hot, and then this aluminum would end up failing. Again, aluminum gets weak at fairly low temperature, so melts at 1200 degrees. It weakens at somewhere around half that or so. So that's not very high temperature. So anyway, you can see that in that area right around where the foam struck, if there was damage there and hot gases were able to get in, it could be a serious issue. These panels are a very brittle material. They're not designed for impact. So they do have carbon fibers running through them that make them tougher than if it was just some kind of a ceramic material. That's what the reinforced means. It's basically carbon fibers in a carbon matrix. So instead of like carbon fiber reinforced plastic, which is carbon fibers with an epoxy resin or some kind of other plastic material, as the matrix, this is I believe it's a carbon ceramic material. It might just be carbon graphite, and then the threads. I'm not super familiar with reinforced carbon, the material itself, but it's a brittle material, and it's not specifically designed to resist. I mean, it's not very strong on against impacts. Like a lot of fairly brittle materials, at least the matrix part of it's fairly brittle. It doesn't handle impacts very well. So damage to these panels have been seen on previous launches. The expected mission life for these leading edges for these panels dips when you get into this area where the foam strike occurred, and this loss in lowest expected mission life is going to be from impacts and additional wear from heat. So it's a highly stressed area right around where this hit. And again, this is some damage from STS-45. This is some damage, some spalling on the interior of that. So these kind of impacts had happened before and had been fairly serious before. The foam piece for Columbia was estimated from the video footage to be traveling around 545 miles an hour. was flat and 24 inches or so by 15 inches. So pretty good sized chunk of foam traveling at about 545 miles an hour or so. Estimated to hit somewhere in this zone here. So the last piece of the puzzle was to figure out, could a piece of foam traveling at that speed actually penetrate the reinforced carbon leading edge? There's evidence that it could damage it, but could it actually penetrate it? So an air cannon was made to shoot chunks of foam at similar speeds at the leading edge subsystem. And in this video, you can see at the 1 minute 20 mark, there was a test where I believe it took several different tests, and eventually they were able to get one impact that did leave a considerable hole, uh, you know, somewhere about the same size as the chunk of foam that impacted it. And then that gets back to here where you've got, and I believe it was on the bottom side of it, a large hole here that would let hot gases in. So from the evidence, from the magnetic tape, from the data, from the telemetry, uh, during reentry they detected some sensors, some overpressure sensors, I believe, in the tires, left landing gear. You could see how if hot gases were getting in here, it would heat up the landing gear bay and heat up the tire, causing the air to overpressure. There was some loss of sensor data in this area from wires burning through or sensors failing. So there was a lot of evidence that something was going on this left side, and specifically that it was getting hot in there. And then that combined with the video footage that showed the foam strike in this area, combined with the test that showed that the foam in question could actually penetrate the reinforced carbon made it fairly conclusive that this is what caused the Columbia orbiter to be destroyed. So fairly conclusive. Again, you don't really know a lot of failures. You sort of have to with the evidence you have, sort of infer what happened. But it's very very high likelihood this is what caused the loss of Columbia. So who's at fault? Uh, so what you find if you read the accident report is they end up citing the culture of management at NASA and how they listen to the engineers, how they listen to the technical people, how decisions are made about what's a turnaround issue, what's something that should be addressed. And if you go back to the Challenger report, Columbia report, that's what we're talking about. If you go back to Challenger, you see the same pattern where organizational decisions of an organizational culture was faulted, and that's a common theme in engineering failures. Is there's in the modern era we just know so much about how things fail that there's very few surprises, and we just had no idea this thing was going to fail or fail in this specific way. I mean, there was a lot of that historically, fatigue analysis when machines started turning millions of cycles and metal shafts that were fine for 1,000 cycles all of a sudden snapped in half at 5,000 cycles or 500,000 cycles. That's a new phenomenon. The Tacoma Narrows Bridge, where you had aeroelastic flutter causing a bridge to fail. I mean, that didn't happen on shorter spans, so it wasn't even something they were expecting at all during, the civil engineers didn't know they had to be aerospace engineers or have aerospace engineers involved, or aeronautical engineers, I guess, at the time, in their bridge design. There's failures that happen when you just don't know to even anticipate something. In Columbia and in Challenger, in both those cases, these were both known things. At least they knew that in Challenger, they knew that the O-rings, there's a limit, a lower limit on temperature for the O-rings to conform. It was a known issue. It was something that the engineers at I believe it was Morton Thiokol knew specifically this could be an issue, and were trying to get NASA's attention on it, and NASA management just didn't stop the launch. And then a similar situation happened here with Columbia, where they knew something was wrong. They knew it had happened previously, and it hadn't caused a complete failure. But it's close enough that it should be very, very concerning. So, in both cases, organizational failures were essentially cited. Cultural failures were cited. And this just doesn't happen just at NASA. This happens there everywhere uh, where there's a high stress environment, where you're doing risky things, you're doing difficult things, you're doing complicated things. And there's lots of opportunities for things to go wrong, and lots of things will go wrong when you start doing risky, really high work, high technology, high complexity, high risk, high reward type things. There's going to be lots of things that need to be fixed at any given time, not just one or two. And at some point, you have to prioritize things, and it can get hard, it can get difficult. So, I've been in a few situations in the industry where I've had to make hard decisions, and it's it's something you'll all face. And some big, some small. Some of you will go work for NASA or go work for SpaceX or go work for General Motors or Ford and deal with systems where people's lives are at risk, and you have to make difficult decisions sometimes. So, at the end of the day, you've got to live with yourself as an engineer, and you got to live with the decisions you make. And I think what you'll find if you talk to people or hear interviews from people who have made the wrong decision, or tried to get help and weren't able to get help and had to live with the consequences of something terrible happening, and they always wish they could have done more. They always wish they could have uh, gotten the help, or fixed the problem, or not ignored something, or not just assumed things were going to work out. It's tough in engineering because people's lives are often at stake. So there's been a lot of effort in trying to sort of formalize what the responsibility of an engineer is. And a lot of that gets around being a professional engineer, being licensed as a professional engineer. And part of that is to agree to a professional code of ethics. So NSPE code of ethics is a set of expectations for you as an engineer. And this is something that here in the U.S., if you're working on systems that do affect public safety, you will have to usually be a professional engineer. If not, a PE at your company will have to sign off on the work you do. And that engineer will have to review your work and ensure that these things have been done. So uh, it's I don't know. It depends on what industry you go into. Some of you won't ever deal directly with things that affect public safety, or health and safety in general. Some of you will be PEs, and that's basically all you'll end up doing. So there's a lot of mix in mechanical engineering. It's a big mix. In civil engineering, almost all of the engineers have to be PEs to even get any work done, because it's essentially all public welfare. But for mechanical engineers, a lot of you don't even really need to be a PE, and will have no need to be a PE. Some of you will. There'll be a few at every company that sign on to be PEs. But even if you aren't a PE, you still have to take responsibility for the decisions you make, and you still have to do your job and do your job ethically. And if there's a problem, it's always better to just address it and fix it. And usually, the sooner you can fix it, the better. Uh, so anyway, that's it for today's lecture. Hopefully, that's something to think about while you all are getting started on, or start your careers here in a few years. Something to always keep in mind when you're working on systems is things go wrong in engineering, and you've got to make decisions, and the decisions can be difficult at times. So, but always sort of err on the side of caution and doing more rather than less, and engineering. So, especially when you're dealing with the safety of people. So that's it for today. Thank you all.